I'm just going to take 1 minute to give the rationale for the importance of organising data, whether it's MRI or MEG data, according to the BIDS format. I believe that that's going to cover how you do that practically at the CBU for MRI data. In the future, we'll have Mate talking about how to do it for MEG data. But the rationale is that, as I'm sure you're aware, every paper published at the CBU, you are required, is a strong word, but expected to share the data. And if it's imaging, the best format for sharing data is these days BIDS. And indeed, more and more journals, it's not just a CBU, more and more journals require that when you submit the paper includes a link to somewhere, whether that's Figshare or GitHub, or it can be the CBU, some place where even the reviewers can get the data. Just an example, I'm not reviewing any papers these days that don't give access to data and code. It's they're not empirical. Anyway, BIDS is an internationally recognized format for organizing image data, MRI, MEG, and in fact, it also covers behavioral data, although you don't often see it being used for cognitive or behavioral data. The other reason is that more and more analysis packages like fMyPrep or SPM or I imagine FSL can read directly from BIDS. So all the meta information like things like the TR, fMRI, the echo time is all stored in these what are called sidecar files or metadata files, JSON files, so that you don't have to specify anything as a user. That information you need should already be in BIDS format. So you just point your analysis software to the data and it can read in everything it needs. And that's why we recommend that you convert the raw data, which is HeuDiConv in case of MRI, or FIV files in case of MEG, that are, when you do the scanning experiment, they are dumped into MRI data or MEG data. That's the raw directory folders here at CBU. The first step you do before you do anything else is convert those files into BIDS format in your local project directory. Trust me, it's painful doing it later. Better to do it at the start, even though it's a little bit tedious. It is important. If you want to read more about BIDS, the complete specifications are online. You search, how do I represent this in BIDS, and there'll be information there. So that's what I wanted to say, just to explain why Dataset and Mate have kindly put a lot of time into writing some pages on our wiki, or linked GitHub pages, I found, but linked from our wiki, that walk you through how to convert the data from into BIDS format. So that's going to go through the instructions she wrote a few months ago. But yeah, we owe thank you, Datsa and Mate, for doing this. Right, over to you, Datsa.
Okay, so Mate couldn't make it today, but well, I will show also where his tutorials are, and I will walk you in more detail through tutorials for MRI data. So, as Rick said, Mate and I wrote some tutorials. So if you go to our imaging wiki, imaging CBU, imaging wiki, and then in resources, if you click on BIDS tutorials, then you will be brought here. And we have put our tutorials on a GitHub repository, on our CBU GitHub repository. So there are two tutorials, one for MEG and one for MRI. So they are quite detailed, and I will not go through MEG because I'm not that familiar with MEG myself, and Mate wrote quite a detailed tutorial, so please, and maybe at some other meeting we can have another micro workshop on where Mate can go into more details about his tutorial, but it's basically telling you what you need to do and how to do it. That's quite detailed. And similarly, I have written a tutorial for MRI data. And I have been quite detailed here, so I will not read it all through today here, but I will just imagine that I am somebody like you who have collected the data and I don't want to convert it, and what do I do? So, yeah, regarding installation, so our tutorials are meant for running for CBU users. So we are assuming that you are doing the conversion on or CBU cluster. So if you do the conversion on the CBU cluster, for MRI, at least you don't need to install anything really. Everything is already ready there. If you are not running it from the CBU cluster, if you are from the psychology department, some other department, or if you have, well, some other reason you are not using the CBU Linux cluster, then you need to install a couple of things, which I have described here. But I will today assume that we are running it from the CBU cluster. So the first thing you will need to get, we have included a sample code here, like I have included sample scripts how you can do the conversion. So you will need to get these scripts from the GitHub page into your local folder. There are a couple of ways you can do it. Probably the easiest is to clone this repository. Even if you don't need MEG or MRI, you can clone it and delete it. I just think it's easier. Otherwise, you can just go and download file by file or something. So if you go here, you can either download it as a zip. In this case, I will actually clone it using Git, because on our Linux node we have Git installed. And I will use VS Code. We had a VS Code workshop last week. So we have it now on our CBU YouTube channel, so you can have a look at it. But you can also log in through X2Go. It doesn't matter how you get into the CBU Linux cluster. You can use X2Go or VCN, or I'm here using VS Code. So in VS Code, I have installed SSH remote extension, and then I can just connect to the login node. So it's similar as if I was in X2Go, just instead of X2Go, I'm in VS Code, and I have now collected to login node K03, and I can now clone my repository. I can either do it through a command line, or I can do it here. I will just do it here. Paste that, and then I will point where I want it to be. But I want to be downloaded. Just download in my imaging folder. So it's cloning, and I will open the repositories that I just downloaded. Zoom in. So this is everything that was on the GitHub repository. So MEG and MRI, so there is our README file. You want to README, but README probably would be easier to just keep it open here and on the website and go through. So there are the code samples. So the next thing what I will do, so I also have my fMRI project directory. Apology space. Sure. My fMRI project. So that's for my project. There isn't much at the moment. Just my project code and the CBU codes of the participants that I have scanned. So what I want to do is I want from this repository, from the MRI code examples, I want to just have this code folder into my project directory. So there are several ways you can copy it. You can use a command line, or I will just do it here with that copy paste. And now I have these code examples from Git repository into my project folder. I can also now remove this Git repository, because I just needed the code examples there. And now I have my fMRI project. I have already some code examples for bits conversion. So let's now have a look at the tutorial. So near that far, so where are my raw data? So you can find your raw data from a project code, if you know it. So I will type it in the terminal. So my project code was MR 13008, and there is no match for such.
Got a 0.
Yeah, 10 is missing. So these are all my subjects that I have scanned in this project, and each subject has a unique CBU code. So that's unique CBU code. Even if you scan that subject in repeated sessions, it will have a unique code for each session. So what does it contain? Just have a look at one example. So this raw directory contains all the scans you have done for this subject. So we have done MP range and
So they're all in a subdirectory with the date and time.
yes, exactly.
If you want to check the date and time.
Yeah, so if you look at all your subjects, so there is a CBU code that you should write down, and then for each of them there is a subdirectory, like here. So that was the main directory with the subject code and the MRI code or project code, and then they are all in the subdirectory based on when the scan was made. So this was in 2013, so 11 years ago already. So that's an old data set, and that's a time when it was all collected. And all the scans that you did for this subject, so there were MP-range and 8 EPI, so these are functional scans and 2 field maps. And the channel localizer, you can ignore, this is just for the scanner thing. So these are this, what we collected, and they are in DICOM format, so DCM format. So for MP-range, it will be 1 file per slice, and for EP images or functional, it would be 1 file for volume. So what we need to do is, before, well, when we start to analyze, the minimum that you need to do is you need to convert these DICOM files to nifty images, to nifty files. And another thing is you need to organize these files somehow. Of course, you could just organize and leave the folder names as they are here, exactly the same, or you can do a better way, and that's where the bit standard comes in. It basically instructs us to organize our files in a standardized way. So in an essence, how it would look is where is Zoom? Okay, so these are our raw data that are shown. They come, each scan type is in a folder with these DICOM images, and you need to organize them in a specific way. Often we decide our own structure, but the bit standard basically tells us how we should organize. So they should be organized by subject. Each subject's scans are in subject directories, and then anatomical scans are in ANAT, and functional field maps are in FMAP, and functional are in FUNCS. And how you name these folders, so that's according to bit specification, and how all files are named also according to bit specification. And they are in a nifty format, and each nifty file is accompanied by JSON file as a metadata file. So how do we get from this raw data to this nicely organized data? There are several ways. I recommend to use, there are several packages also that semi-automatize this process. And in my tutorial, I have...
But just before you leave the slide, can I just make a comment?
Sure.
So you'll see that each file name in bits consists of a key and a value. So subject -1 is a sub is a key and then the value, and then acquisition. Sorry, the example down here, task is also a key value and standard name thing you have to have the name of the file, and then you can call it whatever you want. Is face recognition. And then run is another standard key, and then it is numbered 1, 2 for each of the runs. And underscore bold is also tells it there's a bold in weighted images. So as that said, the file names have a particular format of key value, key value, key value, and you have lots of them. But these are ones that are required. So,
Yeah, thank you. Essential point.
Just to add, so you talk about multiple sessions, you can have another folder after the subject, which is by session, and then you have a key value for session.
Yes. Yeah, so if you had multiple sessions for the same subject, you would have a subfolder ses and then session number, let's say ses01, and then in each session there would be a similar like here.
so session means a separate scanning episode.
Yeah, when a
Within
participant went into scanner, went out.
Within each session, you'd have multiple runs.
Yeah,
So mine is like 12.
yeah. So if
Well, block
participants,
also means within a run, you have blocks of two. So block is normally a period of one task or one stimulus. So you have a block of faces and a block of scan faces. You can have many blocks per run. A run is when you start and stop the scanner. So a run is a period of continuous scanning. And the session is when you take them out, put them back in a day later or an hour later. So yeah, block, run, and session are different things.
You can also, you don't have to put a numbered value to session.
Yeah. It can be anything you want.
description.
Yeah.
So in my pages, I can put acute or chronic or something like
yeah. Exactly. So to find your scans, you need to know your project code. And you need to know so each time you scan a participant, write down this CBU code for the participants, and then create something like I have created here, this subject list. So here I have 21 subject, and I have written their CBU codes, how they appear in the MRI on the scanner server. So, and now, so in my tutorial, I recommend you to use a HeuDiConv. There are several converters available. I have put a link here, but I recommend using HeuDiConv because it's very flexible. And so what does it do? Is basically it converts the DICOM files to NIfTY format. That's the minimum we need. It generates the corresponding metadata files. It renames the files and organizes them in folders following bit specification. And it generates several other JSON and table files required by BIDS. We'll see it later. And the final result would look something like that I've already shown in the previous image. So how do we start to do that? First of all, you need to know what sort of scans you had in your project. So if you collected the data yourself, like Maher will probably know very well what type of scans you acquired. That you acquire a T1 scan and how many functional scans, whether you acquired field maps, or maybe you also acquired diffusion-weighted images. So usually if you collect the data yourself, you will know it. If you don't know, you can always ask your supervisor or radiographer to make sure. If you get the data from somebody else, and it's maybe less easy to, and not so easy to know what type of scans you had. And so basically to tell HeuDiConv how to convert from raw to bits, you will need to know what scans you have and some basic parameters what you have in these scans. So you can, of course, maybe you know all these parameters yourself, but if you don't know, the first thing using HeuDiConv, what you can do is to discover your scans. Basically, you can discover what type of scans you have, and it will give you a table like this, basically of the scan types and some parameters that you had there. So I will now do that. So DICOM discover. So I have it here from what I got from the BIDS repository. So what you need to do here, you only need to change your project path, which is, in my case, this one. I'll just copy this and change it to that. And then you need to, to discover, I will just use one sample subject. So we will discover, because assuming that all your subjects had the same type of scans acquired, we can just do this discovery for one subject. And I will do it this was my first subject, the previous was a pilot. So I will write, so this is a pass to the raw DICOM, so your MRI, CBU, and the CBU code and project 4.
Can I ask a question? Often things don't go ideally, and one of your subjects has an extra session which was aborted because that went wrong, you restarted. So sometimes you can't assume that every subject's exactly the same.
Yeah.
Could you discover on a CBU star basis, or how do you cope with the fact that one subject may have a different number of sequences or an aborted sequence?
Well, if the aborted sequences are EPA sequences, then it's not difficult. Maybe it will be obvious later if you didn't. So what could be different? So if they didn't have field map, for example.
Yeah, they might be missing something.
So basically, when you do the discovery, try and do this DICOM discovery for the participant who has the full data acquired, so that you discover all the files that all the scans that needed to be there. So do the DICOM discovery on subject which had a full set acquired. So
usually the participant doesn't have it, it just skips it. So
yeah, so later it will skip it, but to discover what you have, what you need to.
More troubling is the case where they have, I don't know, 8 runs and run 5 has 2 DICOM folders because it was aborted halfway through.
yeah, so you can filter.
Yeah, I will show the filter later, yeah. So we are now just talking about discovery. So first we just want to discover the full sets that needs to be there. So do it on a subject where you are sure that all scans were acquired. So that, and I will put where I will just put it in my output in the work directory. So after that, you don't need to change anything in this code. So assuming that you are running it on the CBU Linux node, you have already created this HeuDiConv environment, which contains all the packages. And basically, the HeuDiConv is just a small, it needs some commands like this. So you specify the raw DICOM path where you want the output to be put. And basically, heuristics we will come in the next step. But at this time, I just want to discover all the scans. So I say convert all. So I will discover all the scans that are in that raw path and subject ID, and I don't want to convert at this stage. I don't want to convert them to Nifty yet, and I want that be in bits format, and that's all. So I will save this, and then you can run. So I will move to the code and make sure that these are all my scripts. So I'm now in that folder, so I can just run this DICOM discovery. Let's hope it runs. So it's now analyzing 2000 over 2000 DICOMs. And now it already did something, so I will focus here. So it created this work directory where I specified it to be, and it creates this hidden folder. So it's a hidden folder starting with HeuDiConv. In my tutorial, all these steps I have described in more detail. So you should also read through the tutorial, and it's described everything how you can see your hidden folder. Here I can fortunately see it. So it's in the hidden folder. It has created here the hidden folder. It has created this DICOM info TSV file.
So TSV is a tab separated value file.
Yes, so
The tab is delimited.
exactly, it's like an Excel. You can open it in Excel if you want. I'm just open here in this code. So it gives you the protocol name of all the scans that you had. So this is the name how radiographer put it in the scanner when the scans were acquired. What the name was, how the radiographer defined the scans, and then some basic parameters, the dimensions, TR, TE, and so on. So what now you can look at this table and you need to decide which scans you want to convert to your bits format, which scans you need for your analysis. You don't always need all the scans. Let's say you have acquired maybe diffusion weighted, and maybe for your project you are not analyzing diffusion weighted images. So you don't necessarily need to convert them. In this case, well, I can ignore the first two, these are just for the scanner, but I want to convert the rest of them. So MP-RAGE for 8 functional scans and 2 field maps. So what do we do next? So after we have done the discovery and gotten this table, the next is creating a heuristic file. The heuristic file basically will tell HeuDiConv how to convert from the raw to bits. So this is bits heuristic. That's a Python file that you need to fill in. So you need to basically create this structure. Like, so we want to convert the anatomical scan, field maps, and functional. So in my experiment that I'm showing here, it's very similar to the one I described in the tutorial, so very easy for me. So I also have anatomical scan. Let's put it here so that I can see it. Screen a bit small. But yeah, so also I have anatomical scan, so this will be my anatomical. And these keys are, so these need to follow the bits format. It can be anything. You can also make your own file names. So just in this case, we want them to be in bits format. So this all, as Rick said, so this key value pairs need to be. So if you are not sure, you can, you need to check the bit specification. And you can use this example heuristics, and there is some other example heuristics that I have added. And if you have some additional scans like the diffusion weighted, you would check in bits specification how the file names should be here. But so for
also, yes, you can play as a bit, but obviously you can't break the bids format. If you're not sure, even after looking at the protocol for bids, there is a bids validator you can run. So basically, there's a little package online you can drag your directory to, and it will check that it meets the bids format.
we will do it at the end. Yes.
If you've got incomplete data sets because you've inherited them from somewhere else, I'm definitely asking for myself. And you don't necessarily have all the information that you require, so bits validator or spec. Is it better to put your data in some sort of incomplete, imperfect bits format? Is that still acceptable practices for data sharing when it's impossible to be done?
I think so, yeah.
I think so. I mean, you often get bids warnings which are not critical. If you can also get a bid, this is not compliant at all. But most of my experience, a lot of it is, if it's just missing data, it's a warning that you haven't got the particular value for this particular subject or whatever. But I think even if you have failures, I still think it's better than not having it at all. It's for that.
I think it's also like, it depends on how much information you want to put in. So, I mean, in principle, you could put in lots of key valued information, which are just very specific for that scan.
Yeah, here I have put the basic.
Yeah, they're not necessary. It's actually a lot of some books, quite a few of the details are in JSON file if it's extracted from the DICOMs. And it's really, you want to just point to things that are very specific. I think if you acquire the data in a non-standard way, then there's the ACQ key that you can just write something. This was acquired in a slightly different way, or the data was reconstructed in a non-standard way. You could just write something about that. So it's kind of just flagging in sort of important things that are relatively specific and idiosyncratic. But you can put as much information in that.
Yeah, here I have put the minimum, almost the minimum. Like for anatomical, this would be the minimum. So always as a minimum you need. So this basically specifies that the anatomical, this MP-RAGE file, it will go to sub and subject ID folder, and then a subfolder on it, and the file name will be like this. So sub, subject ID, and T1 weighted. So that's a bit specification for T1 weighted anatomical image. And for field maps, I have added, like AJ said, we can add another things, additional tags or key values. I have added additional here, acquisition functional. It's basically is specifying that this field map was acquired for functional image. I will need it later, basically, because we acquired field maps for functional images, and then it adds in JSON files, it will add that these field maps are intended for the functional images. That's why I have put it here like that. And if we have field maps, if we have two field maps, then usually one is magnitude and one is phase. If you're not sure about that, ask your radiographer. So I have one of the field maps is magnitude and phase. And for functional, so I have 8 functional runs, so I also need to specify how that will be called. So it will go in func subfolder. And here for functional, I need to specify the task name. So in my tutorial example, it was face recognition, but in the current that I want to convert it, it's actually cognitive control. So regarding these, in BIDS, the hyphens and underscores have a special meaning. So I can't now type cognitive hyphen control or cognitive underscore control. So underscore links key value pairs, and hyphens links the key to the value. So I can't, so it needs to be single string. But I can use a so-called camel casing, so I can write cognitive control, so I can use a camel casing, but I can't use like underscore here or hyphen. So you need to specify your task name. It can be REST if it was a resting scan, or something to identify it mainly for yourself. Because sometimes we have multiple tasks as well in that one. And here I will add that, so I have eight scans, and it will just add a run number, so run, and then 2 digits, so 0, 1, 0, 2, like that, and the suffix is bold, so that's according to bits. And then I create like a structure, dictionary with so empty one, and it will be filled in. So the next thing that you would need now is to tell in this heuristic to HeuDiConv how to identify. So it will need to know so which scan needs to go into NAT folder, which is a field map, and which is functional. And how you do is you define these rules. And for that, you can look for advice in the tables that it was created in DICOM Discovery. So how to uniquely identify your MP-RAGE scan? Well, we only have one MP-RAGE in protocol name. So here we can just put if MP-RAGE in protocol name, then add it to the NAT list. For field maps, we have 2, so it's not enough if we say that if field map in protocol name, we need to specify, so one is magnitude and one is phase. And magnitude, so the only difference between the 2 is, if we look at the metadata, if you look at the metadata for field maps, so all the parameters are the same, the only difference is dimension, the third dimension. One is 64 and one is 32. So to uniquely identify which one is magnitude and which one is phase, the magnitude has a larger third dimension usually, and the phase has a smaller.
Just to emphasize, you don't have to worry about this if you're using the standard CBU sequence, because the code that's a sharing handles it all for you. So it's only if you're using a non-standard sequence that you need to edit this part of the.
Yeah, but like in this case, actually in the tutorial, I was using one of the CBU datasets, and this example is also CBU dataset, so there are some changes. So here I actually need to change this dimension to 64 and this one to 32. If I don't change it, it will just not find, it will not convert, because it will not find this. So the 64, there was a hand, yes?
Yeah, so what you can do, Rick, that's slightly about to say this, but to answer your question about how do you convert an image that, or how do you avoid mixing up scans that have been aborted, we always set div 4 to be the total length of the completed run.
Yeah.
So that means
will work if
this will be aborted.
that would work as a sequence random completion, but maybe you find at the end of it that the subject has not done the task, or the button presses weren't recorded and you run something again. There are always situations where it's hard to fill it just on the dimension.
Okay, yeah, sorry, I thought you meant solely.
Well, I didn't know, but that's just we've done a lot of this for CamCam, and it's horrible to.
I guess in your case, ambiguate based on time caps.
Well, they're doing it, yes, but just pointing out that not in the real world, it's not always a perfect DICOM directory for every subject.
Yeah, it's sometimes quite, also these protocol names, sometimes radiographers mistype something,
Yeah,
and
so
it's not anti-rage anywhere, it's
Yeah, that happens a
something
lot
else.
when you're doing sonography of the CAN. You can guarantee about 30, 40 of those will have typos in the CBU-ID or even the MRI project. It's the radiographer.
Type in the scan, the
radiographer mistypes the CBU code or the project number, even worse. Or he puts it in the wrong directory. So it puts in MRI data CBU or MRI data CAN. Just be careful if you can't, if you've got notes that says there should be a subject 15 there, something, or something code, it's not there. There are things you can do and with IT's help to find missing data, move it in the right folder, rename it. So if the you've already typed in 5 digits rather than 6 for the CBID, IT help can rename it for you. So just beware in the real world it's some of real CBU, it's messy sometimes. There's always manual error.
Yeah, the nice thing about the HeuDiConv is it, if it works for a complete case and you know that this particular case has got all the scans and the data exists where it's supposed to be, and then it doesn't work for another one, and then you can start sort of doing some detective work and say, oh, 1, 3 didn't convert, oh, let me go check this Excel file for that particular participant, and maybe it was.
And it might be that you need to create a couple of these heuristic files for like maybe part of subject, you need to use one heuristic set for another.
Yeah, we have that. If you have multiple sites in one project, so you've got to each site. And all this sort of stuff.
Yeah, but well, here I'm showing the basic, and this is ideal case where everything works perfectly. So, okay, so for functional, so how do I identify functional scans? So the difference between functional is that the fourth dimension is large. So here I can just specify if the fourth dimension, here I said more than 100, so that would be, so let's say assume if there were less than 100 volumes acquired, then we will disregard this scan, it was not complete. So, and also I could specify like hard say 232, but actually not always, and often some subjects have a bit more, some more volumes, and maybe some subjects have 240 volumes and some have 230. So it's better to be a little bit vague about this, but it depends. You need to know your data, really what you acquired. So here I say, if there are more than 100 volumes, then I will assume that's a valid functional run. So this is the hardest part that you need to do when you are converting MRI raw data to bits, basically filling in these heuristics. So this is really just you need to define which scans you want to convert and how to identify them based on your metadata there. And so once you have the heuristics created, then if everything works fine and there is no mess up as we here discussed, then that's very good. So create heuristics file, and I have included it in tutorial. Please read through it. I have included quite detailed information about this other things, and now we can convert our data. So it's a good idea first to start, not to convert all 25 participants all together, just start with the first participant, just to make sure that everything works. So I have included here DICOM to bits single subject. So single subject. So in the single subject, it will be very similar to my DICOM discovery. I will just need to change a couple of things. So basically, the project path is the same as I had in my DICOM discovery. And so I will convert the same subject that I discovered, used for DICOM discovery. Just the output I will put now in data bits, so that's where I will put my converted data, not in the right directory anymore. And I will, so here I specify the heuristics file. So this is a file that I just did the heuristics file. I specify the location of it and the subject ID, and the rest is almost the same as in my DICOM discovery, with the only difference that here, instead of convert all, now I say HeuDiConv to use a heuristics file. So it will look at my heuristics file and only convert the scans that I have defined there and that it can find based on my criteria. And now I want them to be converted to a Nifty file, so that's HeuDiConv uses DICOM to NIX, so it will be converted. And then we can save it and run it. And see, so that is equal to bit single subject.
You have to add the DCM to Nifty X to path, or is it automatically added to path?
No, I didn't need to do anything.
It's the content that.
Yeah, I'm using one environment. So that is a bit single subject. Fingers crossed, so it's now analyzing. Yeah, as I said, it should be pretty thick for one, but yeah, in my tutorial I have described all the things in more detail, so I'll put some links to some things, so please have a look through that when you get started. Well, if you have something like that, that means that everything is doing fine, even if it shows some warnings or something, it just doing it. Yeah, usually it takes like a minute or so for this size of
Mentioned just because when I built it myself the first time, it didn't work because I didn't have it to path. I was like, it's gonna work.
Yeah, here, like, assuming if you're running it on your Linux CBU, I have created conda environment, which includes, and the script, like here I have it in the script, conda activate the HeuDiConv. So if you don't use CBU clusters and you need to, I have put it in tutorial, read through the tutorial, I've added more instructions. So here it has finished and has created, so I will now focus on the Explorer. So it has created now a new folder, data, bits, and we have our first subject here. So, what's that? And yeah, so we have our subject folder, and it has now anatomical with a nifty converted T1 scan and accompanied JSON file. So the JSON file contains acquisition details, and we have field maps, magnitude, phase. And let's see, well, one thing I want to check is whether so is this intended for field? So I want to check whether it generated that these field maps were intended for these 8 functional runs. So that's good, that's what I wanted. So HeuDiConv did it automatically for me. And then I have 8 functional runs, NII and JSON files. So for each NII, there's a JSON file, this acquisition parameters. And also for functional scans, it creates this events file. So in MRI scanner, in our raw MRI data, the scanner doesn't have any information about your task. So you save your events details somewhere else. So if you run in whatever you use for stimulus delivery, so that HeuDiConv, there's no way it can fill your events files automatically. So you need to do it afterwards. But what it does, it creates a template. So it creates a template for you to fill later these files, and it just adds the main what's required by bits that you need for each your stimulus, onset, duration, and trial type, and some you can add some other things. So basically, it adds here to do. So what HeuDiConv it does, it creates some of these to do things for you. So you need to fill in these events from your stimulus delivery program that you use, but it generates these event files for you. And then it also generates some dataset specific files, which we will look a bit later. So basically for single subject, so our HeuDiConv heuristics seem to be working fine. So, well, what we could do now is we could just repeat it for all other 20 subjects. But of course, it's not very efficient to do it subject by subject and manual typing. So we want to somehow automatize converting now all my 21 participants. So how do we do that? So it's a tutorial converting multiple subjects in parallel using SLURM. So that's so basically what we will want to do is what we will need to do is we will need a script like this. So basically everything like this, like here. But for each subject, what will change will be the DICOM path, of course, and the subject ID. So what I want to do is I want to have a generic script, which I have created and called HeuDiConv script. So it looks the same as my single subject script exactly, but at the top I have a list of subject IDs that I will give it to it, and a list of DICOM paths. And so where do I get that list? I can do it like manually, like I have added it here, so you can run it just by adding where your subject DICOM files are and how your subject IDs you want to be. But we can also be more efficient and automatize it better. So I have created a Python file basically where I populate and gather all my raw DICOM paths to all my 21 subject. And so that's in this DICOM to BIDS multiple subjects Python file. So you could also equally well use a bash script file, but here I, as an example, created a Python file. What it basically does is it just will get all my from the raw location that I specify. It will create a list of scroll down. So it will create a list of subject IDs, and for each subject ID, it will have a corresponding DICOM path. And then I specify also which heuristics file I want to use and where to output my data. And this bash command, it will then submit the job. So for each subject, it will send the job to SLURM system and convert each subject to bits. So there are several ways. This is just an example how I did it. So again, you need to put your, just here, if you run it on Linux, on our CBU system, and your data comes from our MRI scanners, then the only thing you need to change is your project path. So that was my, this one. That's my, where.
Those of you who don't know, the SLURM system is just our compute node, so we're going to run it in parallel. So potentially up to 21 cores, or make it 21 times faster and run it one after the other in the login node.
Yeah, exactly. So it will, and you can, while it's running, you can go and have your copy break. So here I specify that's my project path, my fMRI project on my imaging space. So this is a HeuDiConv script, this generic script that I showed here. So it will call that. And I specify my BIDS heuristics that I have created and where I want my output to be. So my project path data bits. Sure, yeah. If you need to leave, I'm recording it, so you can, thank you, Rick. And so, as I said, so if your data come from MRI, from our MRI scanners, then you just need to specify here the project code. And you need to fill a list like that. So I have 21 subjects. So I could know, well, you can either write it manually, fill a list like that manually, and the subject IDs, so these are how they will appear in your bits, converted bits data. They can be anything. They don't have to start from 0, 1, 0, 2. They can be also stay these numbers, but there can't be spaces or hyphens or underscores, but otherwise, but in my case, I just want them to be sequential from 0, 1 to 0, 21. So I could do it manually, or I can be a bit more efficient maybe, and here I have already created. So because I have this nice text file with all my subject codes, and I want them to be from 0, 1 to 21, I will just basically read that text file, and what it will do for me is it will generate this list for me automatically. So it will basically create a list like this, just reading this text file. But yeah, so how you do it? In essence, what you need a dictionary like that. And then that's all basically what you need to do. And it will then, from that list that you have provided here, and oh no, I also will need the project code, of course. I'll comment that out, and the project code is, because that's how it will find the raw path to the raw data, and my project code is MR 13008. Yes, so that's how it will find where the raw DICOMs list, DICOM paths are. So a good idea before sending it to this S-batch SLURM and converting all my 21 subjects, a good idea would be to debug, to basically see what's happening. So because I'm running it on VS Code, I can debug this up to here. So here it will submit it to the S-batch. But before it submit, I just want to check whether it will send the right things that I want them to be sent. So I will So now I can check. So what it did. So here, so my subject list. So this is now my subject list that it generated from my text file. That's how I want to double check just whether it's like you want it to be. So 21 subject, everything seems fine. And because it is sending it to the shell, to the bash script, it needs to be in a specific form. So basically here what the code does, you don't necessarily need to, in my tutorial I have described what the code does, but it basically transforms it, it finds a DICOM path for each of the subjects based on the project code that you specified and CBU code for the subject. Fine. 21 subject. And here it just checks some, does some checks whether there's a heuristics file that you specified exists, and some other things. And then it will send these parameters to this HeuDiConv script that I created. So it will, so this is my script location, this is my subject IDs, this is a DICOM path list. So the list of DICOM paths that it sends to the bash script is basically a string with a space separated for each subject. A space separated the path. So that all looks fine. Good. So that looks good. So I can now run this Python script. You can run it from terminal. If you're using VS Code, you could just now press and run Python file, but if you're running it from X2Go terminal, let's say, let's do it from the terminal here as well. Code. Welcome to this. And now you can go and have your coffee break. You can also use SQ to check. So SQ and your username. So these are, it has submitted now 21 jobs. So one job per subject, and it's now running on our compute system. So you don't need to worry about that. You can check actually also in this code I put where the job outputs are going. So I can specify them to go in the work directory here. HeuDiConv job log. You can check whether there are any errors. For example, if you see after a few seconds that it has stopped, then something is wrong because it should take at least 2 or 3 minutes. But if after a few seconds nothing in your none of your jobs are running anymore, then the problem was an error. So you can go and check this error file. So it's funny. So these output logs, there is an error file and there is out file. But HeuDiConv interestingly puts a lot of information in the error files only because it starts with a warning, but it's just like warning, not an error. But basically it seems fine. It's analyzing DICOM files. And if we check at some, so that's our first subject, so it all looks fine. So these job looks are particularly useful if something goes wrong. If it doesn't convert, then you can go to them and check what has gone wrong. So this shouldn't take too long. It depends. Sometimes it runs just 3 minutes, sometimes 5 minutes. Yeah, so, and in the tutorial, I have added more information about all these things. Also how, yeah, so I will look through it. But basically, yeah, if you run it on CBU login nodes and on from our MRI scanner data, the only thing is that you would need to change in this multiple subject script is at the top here, really. Yeah, so your project path. And you need to provide this subject list, basically, yeah, which I have done it automatically here. I have read it from my subject text file. Let's have a look. Still running, we'll see in data, so it's already, it has already created and generated. So something is happening, 21 subject already. No, so much still running, not finished. We are close to the end, and our data set of 21 subjects will soon be converted to bits. We can just look, a peek. So we have for each subject, we have anatomical, functional, field net functional. Job is done. So very good. So now we have our data converted to bits. 21 subjects, all nicely organized. And what HeuDiConv does, on top of having each subject data, it also adds this dataset general files, like participant file, for example, participants. And that's information about our subjects, age, sex, and by default, they're all in control group. If you had multiple groups, then you need to edit this yourself. And so it generates this participant file and some other things, dataset descriptions that you need to fill. So it adds these to-do things, what else you need to do to fill in dataset description and other things. Okay, so now what we can do is, as Rick mentioned, we can validate the bits dataset to see whether a just converted dataset, whether it confirms the bit standard, and there is an online bits validator where it will not upload any data, it just uploads the file structure basically. So this was my fMRI project, and it has now generated the data bits, and I will upload it. It doesn't upload any files, it just uploads the structure and analyzes whether the file names and the files are what needs to be there. So what do we get here? We get some summary. We have 700 files, a 6 GB large dataset. We don't get any errors, fortunately. But if you get errors, just check them and yeah. So here we get warnings, some inconsistent parameters, which basically is that some subjects had more volumes acquired than others. That's fine. That's nothing to worry about. Warnings are. Yeah, so basically, you can have a look, but this is nothing to worry about. Basically, our dataset is bits dataset now, and now we can share it. Now, first we can analyze it, and a good thing about it is, as Rick said, that when our data are in this standard, in the bits standard, we can use so-called bits apps. Bits apps. Like here I have the link. There are many bits apps where you can just give your data set and use the apps straight away. One of such apps is that you might be willing to use is fMRI Prep, which is an automatic pre-processing pipeline where you just specify the location of your bits data set and it does all the pre-processing for you. And there are other apps like that. And it's not only like these bits apps, but it's also easy for you within a group. You don't need to rewrite your scripts, and you can reuse your scripts easily, and you understand each other's file structures. And when you collaborate with others, it's really no-brainer not to use the bits, not to convert it to bits. Because even if you didn't convert it to this bits format, you would still need to decide, so how do I structure my data? Do I structure by subject folder, by task, by something? How do I name my files? So here's the only difficult thing that you really need to do is have this basically that heuristics file. The filling in this heuristics is the only tricky thing that you need to do. The rest is done for you. And another tricky thing, of course, is as we discussed here, if there is a bit of a mess in your data set, if some subjects can cancel scans or something was named. So you always need to check whether everything is as you want. So go through and check. But yeah, so basically, I think it was quite painless for standard cases, at least. It's really pretty easy to convert your raw data to this bits format where you have data NII and you can start to analyze it. So I hope that the tutorial will help you. If you have any questions, then ask. I think, yeah, so the main steps basically to revise tutorial seems maybe quite long because I have been quite detailed, but basically the main steps is get the example scripts from this repository, customize the heuristics file. For that, you first might need to run HeuDiConv Discover, and then basically update the Python scripts and multiple subjects Python scripts at top to specify your subject locations and execute the script, and then you are done and you are ready to analyze. So that was for bits conversion of MRI data. Do you have any questions? Yeah, and for Meg, so we wouldn't have time now anyway. We are over time much. But for Meg, similarly, Mate has created a tutorial how to create your MEG, EEG data to bits format. So yeah, I hope it helps and it will help, and I really very much recommend you to convert your data to bits format straight away once you have it collected and before you start analyzing.
Thank you.
Thank you.
Thank you.